Hello, I'm Ricardo Malagodi Cagliari, and together with Nideral Mastelari, Renan Ramalho Geraldes, Marcelo Alexandre Leite de Moraes, and Red Wittwood, I'm the author of this paper, System Identification and Controller Design for the Sirius High Dynamic Double Crystal Monochromator at Sirius. This is the outline of our presentation. We start with some context, talking about the Sirius project and the beamlines. Then spend some more time with the system identification, the controller design, the main subject of this work, and finish with some performance results of this amazing machine. This project was conducted at Sirius, the fourth generation synchrotron light source in operation in the city of Campinas. This is the most advanced research facility in Brazil and one of the most advanced light sources of its kind currently in operation worldwide. It consists of an electron particle accelerator that changes the trajectory of the electrons to produce synchrotron radiation, a broadband radiation spectrum with a really nice and small and concentrated beamline. The high dynamics double crystal monochromator is part of some beamlines, the research facilities that are installed along the building to condition the generated synchrotron light, perform experiments, and produce cutting-edge material research science. The first HDDCM is installed at the Manacá beamline. It is located 30 meters away from the light source element and is combined with focusing optics to perform crystallography experiments. The HDDCM purpose is to select the desired energy from the broad spectrum synchrotron light. The target of 10 nanometers RMS in position stability comes from the really small beam dimensions combined with the incredible peak distance between the light source, the HDDCM, and the sample. This breakthrough project targeted an improvement of amazing 100 times in scanning stability to be able to use the most of the new capabilities of the fourth generation synchrotron. The specs and design highlights are summarized in this slide for reference, but unfortunately we don't have time to discuss these in details. Also, we show here a nice picture of the machine opened, where you can see most of the main elements that compose this machine, and also the vacuum vessel that is and covering it in normal operation. But the details are shown better in the paper itself. Talking about the main design target, that's the three main motion axes that we have, but the main design target is this nanometer performance short stroke module, which is composed by 3 voice coils and 3 microsol interferometers disposed in a triangle arrangement to allow to control for gap, pitch, and roll. In this animation, we show the metrology frame, the short stroke, the metrology frame, the short stroke, and the interferometers. Note that by having the voice coils and interferometers aligned, we can take advantage of nice collocated control design properties. In this memo board plot, you can see the result of an identified plant, showing the input actuation forces in columns and the sensor outputs in lines, already converted to gap, pitch, and roll. Here a remark for the MI partner colleagues who helped us in the first identifications and also many fruitful discussions. The first identification was made by injecting a white noise signal in an open loop condition. With this in hand, we can close the loop and start using the 3-point method. As we can see in the block diagram, we inject the signal after the controller and read the signal just before and after the plant. In the second step, we normally apply a multi-sign excitation signal, where many frequencies are injected at the same time. But in our case, we want to go even a step further and use a single sign actuation principle, applying each frequency individually and detailing better some peaks that could not be modeled due to budget restrictions in the modeling phase of the project. By having the plant, we can compute the relative gain array to quantify the level of interaction in the MIMO systems. This graph shows the much higher gain up to about 1 kHz at the main diagonal when comparing to the out diagonal terms, which indicates the low crosstalk between the degrees of freedom and make us simplify the control design, applying the loop shape for 3 CISO systems instead of one MIMO and much more complex system. With the plant in hand, we can now talk about the controller design itself. In this table, there are the main controller design targets, some by the book numbers, and they are 30 degrees of phase margin, 8 dB in phase gain, high gain below 100 Hz, and low gain above 1 kHz. From the identified plant, we can start the loop shaping controller design. First, we identify the desired bandwidth. Then, in this case, we are talking about 250 Hz. Then we add a second order low pass, starting at about 4 times the bandwidth, in this case 1 kHz. Then we place a weak integrator at about 1/5 of the bandwidth, used to increase the low frequency gain and improve the trajectory following performance. Then we place the lead filter centered near the bandwidth frequency to increase the phase margin. We also place some notches in order to reduce the high amplitude and damped peaks, in our case above 1.2 kHz. And finally, we define the proportional gain to make the magnitude graph cross the unit at the desired bandwidth frequency. This is how we shape the open loop baud diagram. Although the baud plot is the most used visualization graph as presented so far, the Nyquist diagram is really useful to help to design a true robust controller. In this case, we can see that our design is not touching the 8 dB circle for any degree of freedom. The sensitivity plot helped not only to identify the high frequency peaks, that they are not being amplified in a desirable way, but also to optimize the trade-off between increasing the low frequency gain and reducing the sensitivity peak. The characteristic Loci was computed to visualize the MIMO performance. This is a good indication that our system is also stable in MIMO. Here is a cumulative power spectrum of the main degree of freedom of the short stroke pitch. This result is an unprecedented result where we see that we achieved the target of 10 nanometers, 10 nanoradians from 1 to 10 kilohertz. Since we are focused in the scientific experimental case where just this energy scan matters, we could still not perform scanning tests up to the machine limits. This is why the graphic shows energy scan velocity in the x-axis. The energy parameter is non-linear in space, but is clearly not optimized in terms of motion. And the scan target was of 200 nanoradians, and we achieved actually for most of the points 17 nanoradians. Those points that are going up to 10 times higher, that means still slightly below the target, they can be truly optimized by means of feed-forward applications. That's it. Thank you very much for your attention, and feel free to reach me out through this email for further questions.